Hi folks, today we're going to discuss the article entitled Proximal Policy Optimization Algorithms, with the lead author being John Schulman. This is an article that was published in August of 2017 and has been cited over 18,630 times. To set the context for this article, we're going to discuss the differences between exploitation versus exploitation and exploration within the context of gold mining. So imagine that you're using a strategy of exploitation where you slavishly exploit a gold vein, but in doing so you miss larger veins of gold and you ultimately wind up at a dead end. By contrast, if you engage in a strategy of exploitation and exploration, you may exploit a particular vein, but from time to time you may reevaluate and explore richer veins. And in doing so, you can realize more gold. And so clearly a strategy of exploitation and exploration is preferable because you're less likely to result in a dead end where you can exploit no gold. One method for an exploitation exploration strategy is the actor-critic method. In this method, there's a critic who tracks whether current activities yield a reward. So for example, does the current mining yield a vein of gold? And then there's an actor who tracks historical activities and updates based upon a success rate of the current activity. So for example, does the current mining as compared to the prior mining yield gold? Now between these two, a success rate will be passed. This success rate being whether there's a high or low success such that a policy needs to be updated. Well, what's a policy? Well, taken together, the actor and the critic track current mining activities against historical activities and update the historical activities as a policy. Now, as implemented, the actor and critic are two separate neural networks, with the former predicting and learning current state, action, anticipated rewards, and the latter receiving an error rate from the critic and updating a learning policy. I'm not going to cover this architecture in detail in this presentation, but I'll put some links in the comments to articles and presentations that do cover this architecture. Much like the problem of dead ends when implementing a strategy of exploitation, you can also have a problem of dead ends when implementing a strategy of exploitation and exploration. And this is really the problem of large updates. What is this? Well, when implementing a strategy of exploitation and exploration, you can actually explore to the point where you explore a region with no possible rewards. And in doing so, you effectively, inadvertently, rewrite a policy. In particular, you want to avoid large policy updates that deviate substantially from current activities or policies, because large updates can result in the exploitation of regions with relatively few or no rewards. And these are known as dead ends. And when this happens, you can effectively change or rewrite your policy such that you effectively lose the historical context that was provided this policy, and you have no ability to get back to this original historical policy. With the foregoing as context, Proximal Policy Optimization Algorithms, or PPO, are really algorithms that are used to control for large policy updates. In particular, PPO establishes a boundary or limit of one's ability to engage in exploration. And really, it's a limit on a policy and changes to policies. Now, the features of this boundary are the following. It's typically continuous as opposed to made of a discrete point or points, as exploration may be unpredictable. It's typically a minimum boundary, and it really kind of scales to success or failure. Namely, if success is anticipated, then the boundary may be scaled back. So this slide actually describes the PPO algorithm. So as the authors state, without a constraint, the maximization of LCPI would lead to an excessively large policy update. Hence, we now consider how to modify the objective to penalize changes to the policy that move R sub t away from 1. The main objective we propose is the following. So this is a lot to digest. Let me break it down for you a little bit. So E sub t in this algorithm, is really an average of boundaries over a number of samples. So really this returns an average boundary for all acts of mining up to that point in time. So basically this defines the average boundary. The min is really a function defining the lower bound for a particular act of mining. R sub t is really a function that identifies changes to a policy as a distance from 1. So really this is a function that defines kind of like what's normal mining activity and resultant rewards and what's abnormal. A sub t is really an estimate of the rewards associated with an action that allows one to scale. So put another way, if you anticipate there's going to be high rewards, then maybe you want to scale the boundary back. If there's going to be low rewards, you want to scale the boundary up. So this gives some flexibility to really the boundary solution. Clip is a function that really removes the incentive for moving outside of the interval. So basically the idea here is that you want to disincentivize certain types of exploration, or you want to incentivize, but you want to do so really within a particular interval. And so this is the function that really does that, is it removes or adds to the incentive. So that's kind of a brief overview of the PPO algorithm. And now we'll get into some of the, philosophical aspects of PPO. So based upon the foregoing, it's clear that PPO is a control application used to really control for dead ends that can arise while exploring. However, another application of PPO is to control for unforeseen outcomes, as these are characteristic of reinforcement learning. Well, what do I mean? Well, one thing that's common to reinforcement learning is that you can have outcomes that were unforeseen. And these outcomes can be in the form of, for example, coming from new game strategies. So for example, there's an algorithm called the TD Gammon algorithm, which implements a form of reinforcement learning. And through implementing this algorithm, they were able to uncover a variety of new strategies that no one had ever seen before with respect to playing backgammon. And you see this arise time after time with respect to various reinforcement learning solutions. So for example, while TD Gammon is one, another one is AlphaZero Go, where there were new novel strategies that were arrived at for playing the game of Go. Now, discovering new backgammon strategies is social good, but there could be applications or uses of RL that result in behaviors that could be socially harmful. And this is where PPO really comes into play, is to really create boundaries to basically stop or limit potentially socially harmful behavior arising out of reinforcement learning-based solutions. Summing it up, an exploitation and exploration strategy allows one to avoid the dead ends of merely exploiting a known reward. The actor-critic method allows one to track current actions and rewards against historical actions and rewards as a policy, and update this policy where there is a high or even low reward success rate. Exploration, however, can result in dead ends in the form of large updates to a policy. PPO creates a boundary to reduce the possibility of large updates by disincentivizing updates that result in large deviations from known rewards and actions. PPO can also be used to control applications to control for unforeseen outcomes that can arise from some implementations of reinforcement learning-based algorithms. I hope you've enjoyed this presentation.